Hello everyone, it's me again, and I'm here to quickly explain aerodynamics in a way that I think everyone can understand. I think all you really need to have is a really basic GCSE physics level of understanding, and I think it will make sense to you guys. So, first of all, let's think about the main forces acting on an object, such as this car, this Ferrari 458, my dream car. So, it's rear wheel drive, so drive from the rear wheels moves it in this direction, but then opposing it, you've got the drag force, you've got a down force, and then opposing the down force, you've got the reaction force, which is where the ground pushes back against it. You've also got lift force. So the aerodynamics concerns stuff like drag force, down force, lift force. There are other types, but I'm not going to cover them today. So let's talk about total drag and drag force. It's made up of two main components. So first one, skin friction. So let's do a little thought experiment. So imagine you're running your hand along some sandpaper like this. You can see that you can think about it, and it's going to be there's going to be a lot more resistance to motion, and it's going to be harder to pull your hand across it because it's rough. So imagine a smooth object such as P Diddy covered in 1,000 bottles of baby oil. If you run your hand along him, it's going to be really, really smooth, and there's not going to be any resistance to this motion. And it's the same for an object. So if you think about the airflow over this object, if it's going to be really rough, the air is going to have a harder time. It's going to get slowed down a lot more, and there's going to be a lot more resistance to the air flowing over it, which means that drag will increase. So it raises a question, why not just reduce the total surface area by cutting off half of it? And that leads us nicely onto pressure drag, which will explain why this will actually slow an object down. So a common misconception, this is what people think about when they think about drag. So the air is pushing back against the car, and that causes a drag force. That's not quite true. There we go. What actually happens? So we've got high pressure here and low pressure here. And the difference between these two pressures is what causes a drag force. So essentially, to reduce drag force, you want to reduce the pressure here and increase the pressure here to make the difference smaller. What do I mean by pressure? So let's think about a balloon. So inside a really inflated balloon, you're going to have high pressure, and you can think that the air inside is going to be pushing, it's going to be trying to expand and pushing in all directions. So all directions is quite important to think about what pressure is. So then low pressure, the air inside is not going to be pushing the same way, at least the same magnitude. So like I said here, low pressure, it's pushing in every direction, but just not as much. You can see here, the arrows are bigger, which indicates it's pushing more. But actually, interestingly, pressure acts at right angles or perpendicularly to the surface of an object. So you can see here, regardless of the angle of the object, it's always acting perpendicularly. So you can see here, pressure, this object it's got a line this way, so pressure is going to act this way. And then similarly here, to act perpendicularly, pressure is going to act this direction. And let's talk about this in a bit more detail. So this looks really complicated, but I assure you I will make it so that it's not. So first of all, the Bernoulli principle. So we've got this equation here. Let's get rid of this. This isn't relevant. P. Diddy can cover this up. And let's also make that constant a number, which makes it easier to understand. So now we've got pressure here, and this is a function of velocity or speed. But I'll simplify that even more. But basically, if speed increases here, so if pressure and speed equals a number, 5. So if speed increases, to keep that equal to 5, you're going to want to reduce the pressure. So let's say this is equal to 3, this is equal to 2. And if you want this to equal 4 by increasing speed, this is going to have to be 1 to equal 5 still. And vice versa. So if speed increases, basically, pressure decreases. So let's talk about this. So first of all, when the air is hitting an object, you're going to have really high pressure, and that's because the air has slowed down loads here, so you're going to have high pressure. And then the air is speeding up, so the pressure reduces, so you've got lower pressure here. But then as it goes over the object, it starts to slow down and slow down and slow down. And here you've got higher pressure. But then what actually happens in a bluff body, which is an object that isn't very aerodynamic, the pressure gets so high, but it actually airflow separates, because it was sliding all over the surface, but actually separates from the surface, and then you get this turbulence, and that actually causes really, really low pressure here, because it's all swirling around in random directions, and it's not sticking to the surface. And then you compare it to a streamlined object, you can see there's still high pressure here, but because this is a more of a gradual gradient over here, it doesn't slow down quite so much, and it stays attached. So the pressure here is higher than it would be on a bluff body. So what it means that the total drag is less. So let's explore this. So you've got pressure, a lot of pressure here, low pressure here, and actually pressure on both sides here, but they cancel out because they're both the same. You can see it's a mirrored object. So this is on a bluff body, an unaerodynamic object. So the result is you've got fairly high pressure in this direction as the total. So streamlined body. So we've got high pressure here, a little bit higher than the other one here, but still less than this one. And again, same here. But what's interesting is, I know I said that pressure acts at right angles. So you can see at this point here, pressure is actually pushing, slightly opposing this arrow here, which has made the pressure here a bit bigger. So there's still, the resultant is still in this direction, but the magnitude is a lot less. Again, this looks complicated, but I will explain it. So I've talked about pressure a little bit. So these arrows indicate pressure. So the arrows are pointing in this direction to start. It's pressing against it. You can see how pressure changes. So these arrows pointing away from it this time indicates low pressure. And you can see here the pressure is really, really low. And then the arrows get smaller and smaller and smaller until it actually turns into high pressure at the back of the object. And why is this? So this is what the surface of an object looks like. So this is as air flows along it. So you can see here as air flows along it. So at the surface of an object, airflow is actually 0, and that is called the no-slip condition. And as you get further away, the airflow increases. You can see these arrows show how fast it's going, so it's getting faster and faster along here. But as it flows over, you can see the speed of the airflow is actually decreasing. It's getting slower. And as we talked about this, so if speed gets lower, pressure gets higher. So you start to get more and more pressure. So we take this point here, pressure here is high pressure, and you've got low pressure. So if you think about how fluid works in a pressure gradient, so you've got high pressure, what actually happens is that the air has stopped moving and it actually goes backwards to get back to flow to where there's low pressure. So it loops around, and this is the point of detachment, where so now the airflow is no longer touching this surface. So that's where flow separation occurs. So flow separation, you want to minimize flow separation, because this is where you get this low pressure zone here, where you've got the big difference. So you want to minimize low pressure down here. So you can see here loads of turbulence, loads of low pressure. And here there's still low pressure here, but it's not as much because flow has stuck on. So here's a case study. You've got a golf ball. So what has actually happened? So you've increased the skin friction drag because you've got these little dimples. But what it means, there's a bit of turbulence, and we go back to this diagram. So if you consider what the turbulence means, is that all the airflow streams are actually mixing about a little bit. So you've got this arrow here, it might swap with, for example, this arrow. So at the surface, you've actually got an increase in airflow. So you see here, this one might swap with this one. So this big arrow is down here. So at the surface, you've actually got faster airstream. And that means that it hasn't slowed down as much on the surface, so it sticks for longer. Eventually it will separate, but it has stuck for a lot longer. And that is why golf balls have dimples. because you want the airflow to stick to the surface. So let's talk about drafting. So you've got two bicycles here. They're moving in obviously this direction. So you've got really high pressure here because this is the first person to hit the air. Then, as I said, behind the person you get this low pressure, as I've explained. And then again, you've got low pressure at the end of the pace line. So you can see the pressure difference between these two is quite high. Between this person is quite high. So you've got lots of drag. But then the pressure difference isn't actually that much. They're both fairly low. So because this person has made the air really turbulent, so there's low pressure. So this person's drag is a lot less, which means it's a lot easier to cycle because there's not as much resistance to motion. And last of all, we'll finish with downforce. So it's the same kind of concept. You're thinking about the resultant force, but in this scenario, it's acting downwards. So what you want is to maximize downforce. You want the highest pressure here and the lowest pressure here. So yeah, why is downforce important? If you're interested in motorsports, you might know it's because you want as much grip as possible on the wheels. So yeah, there's more grip, so you can go around a corner. You don't slide out. You can put more power down as well. And then on the other side of things, haven't talked about it here, but lift is the opposite of this. So if you think about an aeroplane, that's why they angle the wings in the way they do, so that you get lift, and that's why there's the little flaps that open and close, so you can change the amount of lift you're getting to manipulate the pressure. That is everything. Thank you for watching.